Welcome to Spaceverse, your portal to cosmic adventures. For years, astronomers have dreamed of getting a direct look at planets orbiting distant stars. Now, thanks to the power of the James Webb Space Telescope, that dream is no longer science fiction, it's science fact. In a stunning new discovery, the James Webb Space Telescope, or JWST, has captured its first direct images of carbon dioxide gas on a planet beyond our solar system. These observations mark a huge leap forward in exoplanet science, not only proving that JWST can image planets close to their bright host stars, but also unlocking key clues about how planets form. Let's dive into the story behind this incredible breakthrough. The star at the center of it all is HR 799, located around 130 light-years from Earth in the constellation Pegasus. Now that might sound far, but in cosmic terms, it's relatively close enough for JWST's powerful instruments to focus in on it with stunning precision. HR 799 isn't just any star. It's the host of a fascinating planetary system that astronomers have been studying for years. This system has 4 known planets, each of them more massive than Jupiter, our own solar system's largest planet. These alien worlds orbit their host star in paths that take anywhere from decades to centuries to complete. But what really makes this system so interesting to scientists is its age. The HR 799 system is only about 30 million years old. That's incredibly young when you consider that our own solar system is more than 4.5 billion years old. Because of this, the planets in the system are still radiating the heat left over from their formation, a glow that JWST can detect using its infrared instruments. And that's exactly what happened. Using its sophisticated sensors, the James Webb Space Telescope locked onto the system and detected carbon dioxide in the atmosphere of the innermost planet, HR 799e. This is the first time JWST has directly observed carbon dioxide on an exoplanet, and it's a major milestone in space exploration. So what does this mean? Well, detecting carbon dioxide is more than just ticking a box. It tells us something important about the planet's atmospheric composition. The presence of carbon dioxide and other heavy elements in the atmosphere of HR 799e gives scientists a vital clue about how the planet formed. According to current leading theories, there are 2 main ways that planets like this can form. The first is the core accretion model, sometimes called the bottom-up theory. In this model, planets form gradually over millions of years. Tiny grains of dust orbiting a young star begin to stick together. Over time, these grains grow into rocks, then into planetesimals, and eventually into full-sized planets. This slow clumping process creates planets with dense cores and atmospheres enriched with heavy elements, like the ones observed in HR 799e. But there's another theory, gravitational instability. In this top-down model, a region of the gas and dust disk surrounding a young star collapses rapidly under its own gravity, forming a massive planet in a relatively short time. This would lead to different atmospheric compositions and structures. So, which theory is correct? Well, as it turns out, both might be. The detection of heavy metals in HR 799e's atmosphere supports the bottom-up model, suggesting the planet formed gradually like Jupiter or Saturn in our own solar system. But other studies have provided compelling evidence for the top-down model as well. The truth is, planet formation might be more complex than we ever imagined. There might not be a single way that all planets form. Instead, different processes could be at play in different environments. And that's where JWST comes in. By directly imaging exoplanets and analyzing their atmospheres, astronomers can start to determine which formation process is more common, or whether both occur equally throughout the galaxy. Each new observation is like a puzzle piece that helps complete the cosmic picture. The new data also feeds into a larger goal, understanding how unique or how ordinary our solar system really is. William Balmer, an astronomer at Johns Hopkins University who led the new research, put it this way: "Our hope with this kind of research is to understand our own solar system, life, and ourselves in comparison to other exoplanetary systems. We want to take pictures of other solar systems and see how they're similar or different when compared to ours. From there, we can try to get a sense of how weird our solar system really is or how normal." That's a powerful idea. We've spent so much time studying our own backyard, but with JWST, we're finally stepping out into the neighborhood and seeing how others live. And the HR8799 system isn't the only one in JWST's sights. The telescope also recently imaged 51 Eridani, a star system located 97 light-years away. In that system, it successfully captured an image of 51 Eridani b, a cool, young planet that orbits its host star at a distance of about 11 billion miles, roughly the same distance at which Neptune orbits the Sun. Capturing images of these faraway worlds isn't easy. Planets are much fainter than their host stars, often billions of times dimmer. Trying to photograph them is like trying to spot a firefly buzzing next to a stadium spotlight. That's where JWST's coronagraph comes in. This clever device blocks out the light from the star, allowing the telescope to pick up the faint glow of the surrounding planets. Thanks to this technology, Webb can study planets that were previously lost in their star's glare. Remy Sumer of the Space Telescope Science Institute, who led Webb's coronagraph development, described the achievement with pride. "We have been waiting for 10 years to confirm that our finely tuned operations of the telescope would also allow us to access the inner planets. Now the results are in, and we can do interesting science with it. And there's much more to come." In future observations, Sumer and his colleagues plan to use JWST's coronagraphs to analyze even more giant exoplanets. By comparing their atmospheric compositions and physical features to different theoretical models, scientists hope to better distinguish between actual planets and objects like brown dwarfs. Now, brown dwarfs are a kind of failed star. They form in much the same way as stars do through the collapse of gas clouds, but they never gain enough mass to start nuclear fusion in their cores. Because they exist in a gray area between planets and stars, studying them can help astronomers understand the full range of objects that populate planetary systems. Why does this matter? Because giant planets, whether they're gas giants like Jupiter or failed stars like brown dwarfs, can shape the very architecture of their solar systems. As William Balmer put it, "If you have these huge planets acting like bowling balls running through your solar system, they can either really disrupt, protect, or do a little bit of both to planets like ours." In other words, these giants might fling asteroids toward rocky worlds or deflect them away. They might stir up orbits or stabilize them. They might make life more difficult or more likely. Understanding their formation is a crucial step toward understanding the formation, survival, and habitability of Earth-like planets in the universe. And it all starts with images like these, sharp, infrared snapshots taken by one of the most advanced observatories ever built. So as we marvel at these distant, alien giants orbiting HR8799 and 51 Eridani, we're not just looking at other worlds. We're looking back at the forces that shaped our own. And thanks to JWST, the universe is no longer a distant mystery. It's a place we're beginning to truly see and understand. If you want more deep dives into the latest discoveries from JWST and beyond, don't forget to like, subscribe, and join us on this incredible journey across the cosmos. We'll see you in the next one.